My name is Bridget Savitsky, and this is an overview on the extra credit lectures I attended. I attended Why the Universe Isn't Boring, and also the lecture about the Higgs boson. To begin, the main points about why the universe isn't boring includes that the universe is in a state of non-equilibrium, it will tend towards this disorder, and that goes along with the second law of thermodynamics, that entropy will increase in this open system. The universe is nonlinear in that patterns, self-organization, and complexity are a natural consequence of physical laws that exist in our universe. During the lecture, he discussed these patterns, such as the ridges and icicles and the patterns in the sand that the waves make on a shoreline, and also the ridging of the dunes in a desert that the wind creates. He also talked about some other phenomena called the Faraday instability and the Marangoni effect. And we didn't go too into depth. We just watched them in the lecture, but I wanted to look a little bit more into the mechanism that actually goes into them. So first off, the Marangoni effect has to do with surface tension. So when you have a high surface tension in a liquid, it pulls strongly in the surrounding liquid, and a low surface tension will pull less strongly. A temperature gradient, a tension gradient on the surface of the liquid can actually be caused by a temperature gradient or a concentration gradient in the liquid at the surface, and so this causes the tension gradient, and it causes the liquid to flow away from areas of low surface tension. And that's why if you have a glass of wine, you can see what they call wine tears forming a ring around the glass. Faraday instability. This was extremely interesting to look at, but what actually is going on? So in a layer of viscous liquid, if it's placed on top of a vertically oscillating piston, you can see an emergence of a pattern of stationary waves. What's interesting about this, though, it oscillates at half the original frequency that it went on to the surface of the liquid in. And this brings us into talking about something called parametric resonance phenomenon, and it takes place when the external excitation frequency is equal to twice the natural frequency of the system. So that's an absolutely incredible thing that happens in nature. And we see that the waves look like stripes, hexagons, squares, and sometimes can even be even more complex patterns. The main point from the Higgs lecture includes why the Higgs boson explains why electrons have mass, and therefore why atoms have certain radii. And he also talked about the Higgs field and how certain particles moving through this Higgs field attract more Higgs particles than others, giving varying masses. And he also talked about the ATLAS, which is part of the Large Hadron Collider, which is where this proton-proton collision occurs to try to isolate the Higgs particle. It's about the process of how ATLAS worked, but I wanted to go more into depth about what the actual Higgs particle was and why it's so important that we find it. So in matter, there are 12 particles. In these 12 particles, it breaks into quarks and leptons, and there are 6 of each type. And we also have 4 different types of forces, which is the strong force, the weak force, the electromagnetic, and the gravitational force. Theory goes that each one of the 4 fundamental forces has a corresponding carrier particle called a boson, and it acts upon matter. So for example, an electromagnetic field depends on a photon in order to transfer the electromagnetic force to matter. The theory behind the Higgs particle is that particles may not have mass naturally, but instead, when the particle passes through a Higgs field, it actually attracts mass to it. And so a Higgs field actually affects different particles in different ways, and that explains why photons have mass and why other particles called W and Z bosons have a large amount of mass. It occupies the entire universe. I wanted to understand what they saw when they detected the Higgs, and after they collided two protons, they saw a cluster of particles shooting downward, and then a Higgs particle that shot upward that almost instantly decayed into a muon pair and an electron pair. We break it down into past, present, and future. In the past, at the Big Bang, we had the brief existence of the Higgs particle and every other particle for that matter, and they were all dispersed and left to interact with each other for the rest of time. And now, in the present, we have this incredible tendency for patterns to emerge through these interactions, through these particles, even in our universe that tends toward entropy. And in the future, since we have this increasing disorder, there's less energy that can be used to do useful work. And so the universe will eventually simply be a collection of decaying particles that continue to go farther and farther apart from each other with the expanding universe.